Yes. So got it.
All right, so let's get started. Welcome everyone to the AstroAI lunch talk. Today we will have two speakers, and let's see, hopefully we'll have some time for interesting discussions. The first speaker is visiting us from Milan, Nicolò Pinciroli. He's doing his PhD there, and he's gonna tell us about multi-modal neural networks for the study of gravitational lenses. Nicolò and I met recently in Padua. He was very interested to come talk to us. So thank you very much for visiting us.
Thank you for having me.
The floor is yours, and then I'll tell you when you have 3 minutes left.
Okay, yeah, thanks. So thank you for hosting me again. And my talk is about multimodal neural networks for the study of gravitational lenses. So to start, oh, wait.
You should be good.
Yes. So this work is divided actually in 2.5 parts. So let's start with the first part. So the goal of the first part of this work is to discover gravitationally lensed supernovae that are very rare phenomena. Why? Because gravitational lenses are relatively rare, supernova are relatively rare. So the combination of the two is, of course, very rare. For this reason, we don't have a lot of real data of gravitationally lensed supernovae, and we need simulations. Actually, this one is an example of a gravitationally lensed supernova, and this one is probably a real one. But in order to find the gravitationally lensed supernova, we need two components. We need an image that describes the gravitational lens. Indeed, you can probably see here multiple images. And we also need a time series that describes the brightness variation of what we are observing, because otherwise it is more difficult to say whether there is a transient, whether there is a supernova or not. So the input of any kind of network that wants to perform this task must be a multimodal input. So we want also a multimodal network that is able to use this multimodal input. So this problem is initially just a multi-class single label problem with 4 classes: no lens, a gravitational lens without a supernova, a gravitationally lensed supernova of type 1a, and a gravitationally lensed supernova of type CC. So, as I was saying, multimodality is necessary to see the variation in brightness. This instead is an example of simulated data, a multimodal simulated, a multimodal simulated data. And the solution for this problem, the first solution, is developing a multimodal network. In this case, actually, as you can see, there are 3 multimodal networks that I call LONET, and MUNET. I will show you the details very soon. So the idea in this work is very simple. We have 2 inputs, the image and the time series. And then we have multimodal networks that take this input and produce a classification. But this is very similar to a work that had already been done. What is the problem in this case? Well, the problem is that each network is able to see the data in a different way. So, for example, LONET will produce some classifications that will be relatively good, but different than the ones of GLONET. So the idea now is to take the outputs of these networks and put them together to leverage the differences between these networks. And how can we do this? Well, we can do this in a very simple way with ensembling, which means we just concatenate the outputs. Well, in this case, actually, the feature vectors, not directly the outputs. And we just ensemble them using, for example, a very simple machine learning algorithm such as S2M. So let's see the 3 networks in more detail. LONET is a simple network that focuses more on the local features of the images. Why local features? Because we are using a convolutional neural networks, and convolutional neural networks have a limited receptive field. So here is the idea. The image goes through the CNN, The time series goes through a GRU-based network. You could also use LSTM, the results would be quite similar. And then from the time series, we can also extract the mean and the standard deviation, because if we have a high standard deviation, this means there is variability. So this is a hint of a transient phenomenon, in this case, hint of a supernova. Then we take the feature vectors from CNN and GRU and the output from mu and sigma, and we just concatenate them. And finally, we have the classifier that is just a combination of a transformer and a fully connected network. Why a transformer? Well, this transformer was taken actually from another paper that focused instead on remote sensing images, and I've seen it works better than just a fully connected network for this specific problem, because it focuses its attention more on the most important parts of the feature vectors. What is also important is that the CNN and the GRU are first trained independently. So they're trained independently and they're used for classification. Then the pre-trained subnetworks, so the pre-trained CNN and the pre-trained GRU, are used in the overall network. And this also brings some advantages to the overall network, because it starts to learn step by step, let's say. GloNet is a very simple network. It is just a fully connected network. And as you can expect, a fully connected network with multimodal data does not have very good performances. So why is this network here? This network is here because even if the performances are not good, the results are complementary and different compared to the ones of GloNet. So introducing this network in the final assembling is useful because the results still improve, because because the data are processed in a different way. Also, it is called GloNet because fully connected networks do not have a receptive field. They have not been designed for images, so they will focus also not only, sorry, on the local features in the images. And this is also an example of early fusion. Early fusion means that the input after flattening is concatenated without previous processing, while in LowNet we have intermediate fusion, because before fusion, so the concatenation, we have processing by CNN and GRU. Finally, MuNet is very similar to LowNet. The only difference is this part here. So the image goes through a fully connected network and in parallel through a CNN. And these are the results in terms of accuracy. The data sets were balanced, and these results are computed on 4 simulated data sets that simulate real instruments, or well, ideal instruments in the case of DAISY-DOT. So DeepZipper and DeepZipper2 are the 2 competitors that worked on a very similar set of data sets and on the same problem. So as you can see, the performances of DeepZipper and DeepZipper2 are quite similar. And especially for that wide, it is one of these data sets, the most challenging one actually, because the quality is quite low. Well, the most challenging one together with the SNIa, I would say. So in this case, as you can see, the performances are quite low.
Sorry, Nicolò.
Yes.
So what is the downstream task here? Is it to classify supernova, non-supernova, or between different types of morphological?
Yes, I should verify this. So the task here is to perform a multi-class single label classification with 4 classes. No lens, gravitational lens without the supernova, gravitationally lensed supernova of type 1a, and gravitationally lensed supernova of type CC. So 4 classes. So yes, this is better than a stupid baseline, which would just be 25% accuracy, but still the results are not very good. SNIa instead was designed for remote sensing, but still it can achieve better results than DeepZipper. Our networks, however, especially MuNet, reach better results compared to all the competitors, including SNIa, And ensembling yields even some additional improvement with respect to the best of the three networks.
So train on real data or simulated?
This is only simulated data. Yes?
A quick question, so this is great. I was wondering because the reason you're using the second net, GloNet, is mainly for the global features.
Yes.
Because you talked about the receptive field of the convolutional neural network.
Mhm.
However, as you go deeper in convolution, the receptive field grows, I mean, be as big as the image.
Yes.
If you try to, how deep is your low net, convolutional low net?
Well,
How did you try?
it is not very deep because I didn't have time to say this, but one of the ideas was also to have quite lightweight networks that could be trained with very scarce GPUs. That is what I had at the time. So then it is not particularly deep. Also, the images are quite small, in fact. So I think it is probably deep enough. But anyway, I think GloNet is able to focus more on these global features independently on the receptive field, and especially it is able to focus on different details, let's say, compared to LowNet and MuNet. Does this answer the question?
Yeah.
You're welcome. Okay. So there is an improvement anyway that ranges from 3.6 to 11% with respect to the state of the art. Also, there is an improvement with respect to the use of single modalities. So both the images and the time series are necessary to have good performances, and using ensembling is beneficial. So if we consider only two networks or only one network at a time, then the results are going to be worse. There is only one case in which neglecting GloNet does not produce differences, but in general, even the introduction of GloNet introduces some advantages. And well, this is an example. So for example, this one is a non-lens body, and this is predicted correctly. You can see it is non-lens because there is no evidence of lensing in the image. And also, well, you can also say it is probably not a supernova because the time series are quite flat. But let's go to a more interesting example, this one. So this one is a gravitational lens, but there is no evidence of supernova because the time series are quite flat. While here we have a gravitationally lensed supernova, and we can see, well, these simulated data are quite clean, I have to say. We can also see that there is a peak in the time series, so there is the supernova, and there is also the gravitational lens.
So, sorry, so the light curve is for the entire field? Or
it is, oh, yes, it is actually for the central part of the image. It is taken only on the center because we know that the supernovae in case are in the center of the image, because the telescope can be pointed to that specific object, I guess.
Yes, related to this is the time curve an independent measurement?
Can you repeat, please?
Independent measurement, or is it like the same instrument or the same data from the same instrument and just integrated in the central part?
It is the same data, but yes, the image is integrated. So in fact, we have 14 images, and we obtain only one image at the end, plus the time series.
Okay, so in principle, you could also, if you had like computational resources, you could just include the 40 data.
Yes, 14 images, yes. I would say that would not be, I try to do that. And preliminary experiments, just preliminary experiments, show that it might not be a good idea, because if I consider several images, it is true that they contain, of course, all the information I need, but the variation is not so easily detectable, actually. They're quite similar, the ones to the others. While the time series are normalized, so I think giving the time series makes it easier for the network, even if I'm sure that there is a network that can just take the 14 images and use them. Actually, there is a work that uses image time series that does exactly this for supernova. But if I'm not wrong, they consider only a binary classification between lensed supernova and non-lensed supernova, not also the case without the lens. But yes, this is in principle absolutely possible. Yes.
Can you say a little bit more about the forward model? Are you using SIS or SIE lenses without any microstructure, or how do you actually develop these?
I haven't developed the models for the data set, so I'm not I am not completely sure about the distribution of these of the SAE, SAS, and so on. But I would say that there is both SAE and SAS in the simulated data set. But since I haven't worked explicitly on the simulations, I cannot give a lot of details about that, because actually the data set is taken from the DeepZipper paper. I made some changes to this data set. I extended it a little bit. I changed something about the data augmentation and so on. But the data sets are mainly taken by their work. So, but yes, there are both SAES and SAE as far as I can remember. Other questions? No? Okay. And okay, and then this one is a lens supernova, but as you can see in the simulation, there is no evidence. No, I would say, well, there is a small peak there, but there is no real evidence of gravitational lensing. And indeed, this one is predicted as a gravitational lens, but without the supernova behind it. Then this work has some limitations. So, for example, the classification here is limited to the central object. This is, in my opinion, not a big limitation, because you can, if you capture a very big image, you can, or yes, a very big, very big field with many images, you can focus on the individual objects separately. But anyway, the classification that was performed was quite coarse-grained. We had only 4 classes. And so if we want to address a similar but different problem, we need fine-tuning, and this can be expensive because we need to train another network, for example, or we need to fine-tune an existing network. So now the idea is to address these tasks that you can see here. So I would say that the most important task of the ones in this table is counting. Why? If you're able to count the objects in data, you are also able to classify them, to classify this data, because counting is a more challenging task. So if we are able to count, then we already have a network that can also classify everything. And so this is exactly the idea of this part of the work. And I have addressed actually 4 other tasks, classification tasks. So when I consider counting, I consider 3 lensed objects, so supernovae of type 1a and SNCC, lens galaxies that can also that are also in the data. And in the same data sets, I also have no-lensed supernovae of type CC and 1a, no-lensed galaxies, and no-lensed stars that are, I think, less interesting because there are many machine learning algorithms that can, for example, find galaxies. But so if I have this model, I can also perform binary classification of gravitational lenses. So in this case, I would just say there is a gravitational lens, there is not a gravitational lens. Also, I can say whether there is a supernova or not, and the type of supernova, whether it is lensed, and I can also perform a classification that is a little bit wider than the one I presented before, with lensed supernova of type 1a and CC, lensed galaxies, and also non-lensed supernova of type 1a and CC. So the structure of this network, as you can expect, is very similar to the structure of the previous network. The only difference is that in place of having the 3 networks for classification, I will have 3 networks for counting. Each network, as before, is trained independently, and the results are assembled. So here, each network will have 7 outputs, 1 for each type of astronomical body. And for each of these output branches, we will have a count. And you can think about the possible values for the counts as classes. In fact, the counts are big only for stars and can be, well, relatively big only for stars and galaxies. We can have up to 2 stars, up to 2 galaxies. And what is important in this case to address this problem is that when we count, even if the counts are regarded as classes, they're not like typical classes, because these counts have a ranking. So we cannot just use classification, we should use ordinary regression, or something similar to ordinary regression. Ordinary regression sets a rank between the different counts. So if we say, if we predict 2 while the correct value is 0, the error is big. While if we predict 1 and the value is 0, we still have an error, but it is smaller. And so these are the outputs for the counting. So how can we read this? So let's take, for example, star. So for star, we have 3 possible counting outputs that are 0, 1, and 2. We compute the macro at 1 score for these counts, and we can do the same for all the different objects we have for each dataset. And then what I call the average macro at 1 is just the average of all the scores, all the macro at 1 scores we have here. And as you can see, the worst results are obtained for the stick, but still the results are quite high in general, and for stars they are even they're the best ones, sorry, because stars are very frequent in this data set and they are quite easy to identify. They're just points without time series variation, brightness variation. So given this, we can now perform the classification tasks. How can we do this? Well, original in this case, so these ones are just macro at 1 scores as shown before. So original is what we obtain if we just take the counting neural network and extract the classification from there without any kind of fine-tuning. Fine-tuning instead is just a very simple, lightweight fine-tuning of the results we had obtained before. So the original results, when we want to say whether there is a gravitational lens or not in a sample, are these ones. And on average, on the 4 datasets, we have 85% F1 score. While if we try to address this specific task without a very expensive fine-tuning, so using just a machine learning algorithm like SWM or random forest, we can, we can obtain this, we can obtain these results. So there is an improvement of 6%, about 6%, by just using, for example, SVM or random forest. The results are quite similar on the final counting output. The same applies for supernovae. So again, in this case, we want to say whether there is a supernova or not, independent on the presence of a lens. And even with the original network that just counts things, we obtain 87% F1. If we fine-tune these results, with a very simple approach, we can obtain about 90% F1 score. So there is a small improvement that shows that, well, fine-tuning is useful, but still, if we use the original network without other modifications, it is still effective. While if we have multi-class classification of supernovae, how many minutes? 3 minutes? Okay, yes. So if we have multi-class classification of supernovae, here we have we separate the different types of supernovae and we say whether there is a lens or not. The results are lower, but the principle is still the same. So with the original network, we have good results. With fine-tuning, we have slightly better results. And this is an extension that also considered galaxy lenses, and we have also a small improvement. And this is an example. So this is a correct prediction. As you can see, in this case, there is a lens galaxy, there is the central one, a non-lens galaxy, this one, and a star, the small one here. There is no evidence of a transient, so indeed there are a lens galaxy, a non-lens galaxy, and a star, and this is a correct prediction by the network. This one instead shows 2 non-lens galaxies, these 2 ones, and a star that is only partially visible. There is no evidence of lensing, and the prediction is also correct. What about the future work, current future work? So the idea is to use something very similar to estimate redshifts in the same simulated data. And well, the structure would be very similar to what we have right now. And this is also part of the current work. This is not related to this data set actually, but I would like to talk about this for 1 or 2 minutes, 1 minute, I think. So here the idea is this one. So when we have a gravitational lens, this one, for example, was simulated using SIS. So when we have a gravitational lens, we might want to find an analytical description of this gravitational lens, at least an approximated description. Well, this one is an SIS, if I remember correctly, but in general, we can have more complicated gravitational lenses, more complicated models. So we want to find an approximated description because we might not be able to find the actual analytical description of the lens. So a way to do so is using the Roulette formalism, and if we apply the Roulette formalism, that is basically a 2D Taylor expansion in polar coordinates, what happens is that we obtain this image here that is very similar to the exact image, but this small part is missing. And so given, this one, we want to obtain the parameters that describe this one, so it is a multi-output regression problem, and the networks I'm using give this image. So this image is obtained by using the estimated parameters I get from here, that are the approximation, the estimated Roulette amplitudes in the Roulette formalism. And thank you. This is the QR code for the first publication. I actually tried also the first one on real data as well, and it works on real data, but I didn't have time to present this. You can find them in the paper.
Thank you, Nicolò.
Yes.
Thanks. So obviously strongly lensed supernovae are really valuable for time delay cosmography, but time variable AGN are much more common. So can you apply this to non-transient variable sources?
I think so. In principle, yes. I mean, the neural network is multimodal, so as long as you have an image and a time series, it can be applied. The most challenging thing, in my opinion, is having annotated data, because as you can expect, because with annotated data, of course, it is possible to train this model and so on. Without this annotated data, we should resort to something like anomaly detection in order to find the anomalous things, or to simulated data. Yes, in principle, yes. If you have a data set and you want to share it, please.
Thank you. Okay, unless there's one final quick question, let's thank Nicolò again. Thank you so much. Move on to the next speaker. This is Fanny Fan. She is an intern at the CFA during the summer, and she has been working on a machine learning algorithm to do deconvolution and removal programs.
Where should I put it?
You can put that in your pocket and this on your collar.
Yeah.
Sorry. Yeah, right here.
Floor is yours.
Hey. Thank you for the introduction, and it's great to have the opportunity to introduce my work I'm doing last year at the Shanghai Astronomical Observatory. And it is about a novel machine learning algorithm for foreground removal of the EOR signal for SKA. So I'll start with a brief introduction of what is the EOR signal and why it is so important to study it. So this plot shows an early history of our universe, which should be familiar to most of you, but still I will have a brief introduction of it. Can I move to here because I can't see it clearly?
That's fine, I guess, right?
Okay, yes. So after this the Big Bang, the universe is a hot plasma, but as it expands, the temperature gradually cooled down. After 380,000 years after the Big Bang, the universe, the temperature becomes low enough for electrons and protons to form neutral hydrogen atoms. And after that, so with the evolution of the universe, galaxies and other clusters of structures began to form. And after the formation of these structures, the radiation from them will reionize again the gases of these neutral elements. So what the signal we are studying here is the 21 centimeter radiation from the reionization of these neutral hydrogens. Since the distribution of this signal shows the properties of these neutron gas in the early universe, it is important for our study of the early formation and evolution of these cosmological structures. So it is important for us to try to see these signals from the early universe. However, since it is emitted at a very early age of the universe, it needs to go through a long distance to reach us, and there are all kinds of foregrounds in that process. These foregrounds include these extragalactic ones like the point sources and the radio halos, and also these galactic ones inside of the Milky Way, like free emission and synchrotron emission. Also, when we detect this signal with our interferometer arrays, the beam effects of these instruments will further contaminate this signal. So all these foreground noises add up to 4 to 5 amplitudes higher than the ER signal we want to detect. So you can see that clean foreground removal is quite challenging for this task. Therefore, the methods to move these foregrounds have been studied for a long time. For traditional methods, the basic assumption behind them is the spectral smoothness of the foregrounds. And this assumption is more or less correct if we don't take the beam effects of the instruments into consideration. And so this method's basic idea is to describe how the foreground is changing along the line of sight with some specific forms. And depending on if we adopt a specific analytic form in advance, these line of sight fitting methods are mainly divided into two groups: the parametric methods and non-parametric methods. There are a lot of examples of these methods, so I don't have to talk about them all, but I show only two typical examples of them to give you a basic idea of how these methods work. Obviously, polynomial fitting is just about describing the changing of the foreground on line of sight with different orders of polynomial functions. And the famous PCA method is about transform the data to its feature space, and in this feature space, the eigenvectors which the largest eigenvalues show the direction that varies fast. So we can describe the smooth foreground with these highest eigenvalue directions. However, if the basic assumption is no longer correct, of course, these traditional methods will not work any longer. So here I show the plot of the mean absolute amplitude of the clean sky map and dirty sky map, and their differential spectra. The clean sky map just refers to the ER signal plus all the foregrounds, and the dirty sky map is this clean sky map further influenced by the beam effect of the instruments. So you can see from this plot that when we take into the beam effects into consideration, the changing of that is no longer, the differential spectra is no longer smooth anymore. So when this smooth assumption is violated, these traditional methods no longer works. Here I show an example of how these methods is deactivated. So for example, it is a simulated UR map. And if we are trying to recover this signal directly from the clean sky maps, you can see that these traditional methods have not a bad results. However, if we try to recover the signal directly from the dirty maps with beam effects, you can see that it's strongly contaminated by these beam effects of the instruments. So to deal with these problems with these traditional methods, More recently, machine learning based methods are developed, and I show two typical examples of these methods in the literature. And the first one is called the CDAE method, the convolutional denoising autoencoder method. So this network is just having a simple structure of several convolutional layers. And although it is called the autoencoder, actually they don't have a strong distinction between the encoder and the decoder part. It's just about the latent parameters is just the output of some of the convolutional layers. And with the input of the dirty map and output of the reconstructed EOR, they have this result of the recovery of the EOR signal. We can see that it is much better than the previous result shown with the traditional method. And another machine learning based method is called GIMPO21, and it adopted a unit structure, which is very commonly used network structure in these picture or photo processing tasks. And also it can reach relatively good performance on their simulated 21 centimeter signal. So then I will introduce our new method here. It is called Fork EOR, and as is indicated by its name, it has a fork-like structure. And the basic idea behind this design is just that if the main problem is caused by this PSF signal, why don't we put them simultaneously into our network and let the network learn their interrelationship, and then they convert the PSF or the unit effects from the dirty maps directly. So we have two parallel branches of inputs, and it can be either they convert the PSF from dirty maps to produce clean sky maps, or to predict EOR signals directly. So based on that idea, I will then introduce our simulation data sets, network structure, training and testing process results, and some further discussion of these results. So to begin with the simulation data set we are using here is the end-to-end simulation of SK1 law observation for cosmic cloud and realization. And all the settings we are using in these simulations, as well as all the foreground components we are using, is included in this format. And also this simulated data set is available on the link at the bottom, but I think I should create a QR code so better. Yes, so this simulation is also part of the work of our group, but it is not, the publication is not online yet. And I'm not quite familiar about all the technical details about these simulations, but anyway, it is not the main focus of this presentation. So here I show an example of the simulated different maps. Here, so on the top left side is the simulated PSF signal, and you can see the dark region in the center region is just the primary beam effects, and there are some other beam effects in outer regions. And for dirty maps, these black clustered regions is just these emissions contaminated by these PSF of the instruments. It actually have some circular-like structures, but maybe not so clear directly from this post. And for the sky map, the features we see here are dominated by the galactic spin control emission actually, and because it is the strongest foreground signal, and there should also be visible that there are some small points like structures, and they represent the very light point sources out of the galaxy. And for the EOR signal, it is simulated with the public software 21 centimeter fast. Yeah. And so then it is a more detailed description of the network structure. So for the two parallel input branches, we have several convolutional layers. And then the output of these layers are flattened and concatenated together. Then it goes through several dense layers to make the predictions of the clean sky maps or the EOR signals. More detailedly, we have 4 convolutional layers, and the first layer has 8 filters, and that mainly serves to extract the relative information for this prediction of the clean signals directly from the dirty signals we are input. And then we gradually reduce the number of filters of these convolutional layers to form a more compact feature presentation to put into the dense layers. And inside the dense layers, since the dense layers have neurons connected to each other, every neuron is connected to each other, so it is used to discern the interrelation between the future presentation of the dirty map and the PSF, and to deconvolve the PSF from dirty map. Finally, the number of the neurons in the dense layers are gradually increased to form increasingly detailed reconstructed maps. Yeah. So for the training and the testing process, we need to, of course, divide the data into training, validation, and testing set. And what we are using here is to divide each map further into 4 patches, and we pick around 20% from the first 3 patches to be the validation set, and pick out about 30% from the last patch to be the testing set, and the remaining parts are the training sets. And please note that here we shape the data to in each patch to these smaller squares, so that the number of the samples increase. And also we want to the network to learn more detailed features on this map. Yeah, so then after we pre-process and divide the data and reshape them, we train the network and make predictions on test sets. So the results of the prediction on the testing data set is shown on this slide, from which you can see the convolution of the 30 maps on the top panel and the prediction of the EOR signals on the bottom panel. Yeah, and from the pictures directly, you can see that they have good effects of reconstruction of this.
Why do you have that sort of point-like structure on the reconstructed image of the schema? You know, like little dots.
Do you mean that?
Like if
the
you,
grid
if
line
you compare those 2 images, you,
Yes, grid line. I will talk about this more.
okay,
Yeah.
thanks.
Thank you for the question. Yes, and to further quantize quantify these results, we calculate the mean squared error and the correlation coefficient of each pixel on each map. So for the reconstruction of clean sky map, the mean squared error is of all the -4, and the correlation coefficient for maps on different frequencies are higher than 0.96. And for the reconstruction of EOR signals, the mean square loss is of all the -2, and the correlation coefficient on different frequencies is higher than 0.9. So it is not surprising that the reconstruction of EOI is not as good as the reconstruction of SkyMap, because it is of higher order information compared with the clean SkyMap. Yeah, and just like you asked them, we actually can see that maybe not clear enough on this project, but although they agree quite well in general, but there are some differences in the small details. So to further see on which scale can our network reach good performance, we calculate the 2D power spectrum and also the cross correlation of the power of the between the input and reconstructed signals. So from that we can see that actually the regions that don't agree quite well with each other is here or here. There is a sharper degrees in the correlation cross correlation between the input and output. So which corresponding to about larger than 0.5 MPC inverse. So this failure this failure on these smaller scales have several possible reasons. Yes, the first possible reason is the limitation of the size of the convolutional kernel. I didn't mention before, but it is of size 3. Yeah, and also possibly because the limitation of the size of the reshaped data, and just as you asked, the grid-like features is also possibly rooted from this problem. And further, a further question I want to discuss about is that in our simulations we have different weights of PSF. That means that when we produce the dirty maps by convolving these PSF with the clean map, we have different values on different points, and this plot shows that the 3 choices of the weight of the PSF. So in the previous result, I showed the weights of the PSFs we adopt are all the Briggs PSFs. So we want to ask that the network will work on the uniform and the natural PSFs, which are quite very different from the Briggs PSF. So the answer is that the internet network trained on the Briggs weight does not directly work on other 2 weights. But it is easy to do transform training to further that it's also applicable on different weights of PSFs. And the key question here now is how many layers we need to retrain to make it also reach good performance. And after experiments, we see that only retraining the first convolutional layer should actually be enough. And it is also not surprising because we mentioned when we talk about the network structure that actually the first convolutional layer mainly serves to extract all the source information relative to the prediction of signals. So it is not surprising that this layer is most relevant relevant or sensitive to different weights of PSF on this map. And this is the result on the testing data set with different PSFs. Yeah, despite the great differences in the PSFs and dirty maps, the construction of them are relatively all quite good. So this shows the robustness of the network and shows that it is working somehow in the proper way we expected it to do. Also, it has the potential to apply to other convolutional tasks by transfer training. This is quite important because actually in reality, of course, the PSFs will be somehow different from the simulated ones. So it is important that it has the ability to even do the convolution on different PSFs. And here is a short conclusion of my talk today. So I first introduced the EOR signal and the traditional program removal methods, as well as the new machine learning based ones. And I then introduced our new method for EOR, and it can exactly deconvolve PSFs from the DMs as well as it extracts the EOR signals. So the key takeaway message here is, of course, this full structured network with the DMF and PSF as simultaneous inputs. And yes, we can further think about that and have applications on other similar tasks with these contamination noises from the instruments. And here I show an example which is also a work from our group, and I was quite inspired by this work to do my. So it is about using the input of the PSF and the galaxy image to measure the gravitational lensing shear. So yeah, it can predict the galaxy's magnitude, size, and shape from these input galaxy images. And yeah, the result is that even though the signal to noise ratio is quite low, it can predict the ellipticity as well as the shape of the galaxy quite well. Yeah, that's all my talk. Thank you.
Yes.
Hey, that's very interesting work. Okay, so the kind of key systematic in 21 centimeter cosmology is, as you mentioned, is the fact that the foregrounds are extremely bright and you have this chromatic beam, this chromatic response of the instrument, which can bleed into 21 centimeter. So does it make sense to feed the neural network like a multi-channel PSF and a multi-channel dirty image such that it can deal with the multi-frequency information all at once?
Yes, it is just yes, we fit in not only with this individual maps, but complete data cube along different frequencies.
I see. And what happens if you get if you have errors in the sort of chromatic response to the PSF? Because then you don't perfectly know your side lobes at different frequencies. Because this is what kills a lot of 21 centimeter.
Sorry.
So if you're saying if the PSF shape is not the same across all frequencies, how do you incorporate, if your kind of simulated knowledge of that is not correct, how do you?
Yeah, and specifically in side lobes.
Yes, as is shown by this previous plot of the scanner. So the key problem of the traditional methods is just the frequency dependent PSF signals. And that is also included in our simulations. So although I'm not showing the PSFs of different frequencies, they are of course different on different frequencies. And I think the results show that actually the network is able to do the convolution despite the frequency differences of the PSF, as long as they are not as different weights of PSF. Yeah.
Yeah, okay, more questions? Sorry, let me start here.
Thanks for the nice talk. So from my naive point of view, I mean, if I look at the EOR maps, I mean, it looks very much like noise to me because they're like positive and negative pixels distributed kind of uniformly. So if you eventually aim to detect like EOR, I was just wondering, how do you understand if this is like detection from EOR or is it just noise?
Yeah, I may first give a further explanation of this EOR. So these dark blue regions are these regions without strong ionization, and these with brighter colors should be different strengths of ionization. And yes, you are right that EOR signals compared with the smooth foreground is just like the noises with bigger fluctuations on even small spatial content. Yeah, so yes, you are right. From my own perspective, I will also think that all these foreground removal methods based on these simulations have a big disadvantage that I believe if we apply these methods directly on observational data, I believe what we extracted is also the simulated signals instead of what it truly should be. So yes, that's the difficulty of this part. Yeah.
Can I ask
Sure. Sorry.
Yeah, so as you mentioned that the weights of PSFs will also change the distribution. So I was wondering, like, also the shapes of the PSFs, meaning like from the different telescopes, you will have different kind of features. Right?
Yeah.
So I was wondering then, the models that you are using, is it like very telescope specific that we can only?
Yes. Here the simulations we are using is telescope specific because we use the SKA configuration in our simulations. But I think the key idea is that even if it, of course, it is not directly work on other instruments, but the idea of using the detected signal as well as some information from the detector is important. Yeah. So it is even possible to, I think, to include other instruments, in fact, in some other instruments. Yeah, because you can see that the previous deep learning methods are all directly predict the clean signal from the dirty signal. So the instruments aren't their consideration. Yeah.
Okay, one last question, and then everyone's welcome to hang after and talk to them more if they want.
So, just a quick question, so, very roughly, so where does your method break?
What?
So where does the method break?
Where?
Yeah, so every method breaks at some point. And, progress is always, where does it break and then continue. And, it's okay if you haven't checked this, I don't want to put you on the spot. Yeah. Is there anything, so I'm working in the stats department, right? So is there any aspect of this work where you would like to have a wish list, right, of methodology to be developed that could improve this work?
Yes, as I mentioned in the presentation, one first problem we are facing is that it is not detailed enough.
Resolution.
Yeah, the resolution, and it is possibly method the problem of this network design or something like that. But in reality, since it is from my perspective, it's impossible to recover these signals in such a detail if we are doing this task directly from the observations. Yes, yes, and I think another key problem here is just as asked by her previously is about how to go from simulations to real data, because in real data we don't have comparison of labels. Yeah, we are it is just a blind task, so and it is quite difficult to say if our prediction is correct or not correct. Yeah.
All right, this is Fanny and Nicolò again. Thank you so much. There's some sandwiches left.